Okay, so am I audible and visible? Yes. Am I audible? Am I audible and visible? Okay. Yes. Thank you so much. We were discussing this asymptotic analysis and this order notation we were discussing, order of n, or in general order of Gn. Okay. Order of Gn could be anything. Huh? Not audible? Okay. Is it audible now? Okay. Okay, so this order of n we have seen here, and that is coming from this searching an array. So this is the searching problem, and from there we have seen how this this expression is coming, 2n plus 3, and then we have seen that this is boiling down to order of n. So this n is, in general, this is Gn. Okay, this Gn could be n square, or n power k, whatever. So that we have seen, and in the last class we have seen that, okay, this is this program or this pseudocode. Okay, this is searching one integer t in this array, okay, whether it is present or not, right? And we have got some detailed analysis. So statement by statement we are doing this. Okay, statement by statement, how many times each of the statement being executed, okay, including this statement, this for loop, and inside the for loop how many times all statements being executed. But in general, whenever we'll be analyzing any algorithm, whenever this we'll be analyzing any algorithm, at that time we do not need any kind of detailed analysis like this. Okay, any kind of detailed analysis. You see, this for loop, and then whatever inside this for loop being executed, if there is no other loop, so this ultimately, this whole for loop is boiling down to this order of n. And instead of looking at this statement, this for loop statement, how many times it is getting executed, actually how we are measuring this time complexity of searching is because of this, okay, this statement. How many times we are comparing that number to be searched with the array element. Okay, so this is the indicator term here, or indicator statement. That means we are analyzing this algorithm in terms of the number of comparisons happening. Okay. So that's why this is the representative statement for this. And how many times the number of comparisons happening, how many times we are seeing that, okay, this is n times these comparisons happening. Okay, so this n will be actually determining this the complexity of this for loop, complexity of this for loop, right? So in the next time, whenever we will be taking up examples, at that time the detailed detailed analysis like this we will not be doing. We will be measuring in terms of, say, number of comparisons happening, and that number of comparisons, which statement is contributing that fact, that statement will be the target point, and definitely that is coming within this for loop. Okay, so this for loop structure, within the loop structure, which statement is contributing that fact, we will be looking to that, and then we will be determining how many times that is happening, and based on that we will be determining the time complexity. Okay, and that way our life will be easier. Okay, so take a look at this next example. So this we have seen here how mathematically we are doing this. So another example, so as usual, this is based on this class is based on CLRS, and then obviously this team rough garden. Okay, so this rough garden, anytime I get some kind of leisure, that means when I get some kind of leisure time, I read CLRS, and I go to this professor's website, Tim Rough Garden. He was in Stanford University. He was in Stanford, okay, and now he is in Columbia University, because that Columbia University may be closer. Huh? Sorry? Anybody saying anything? Hello? Muted? Oh, okay. Okay, so this Tim Rough Garden now in Columbia University that I was talking about. Anyway, so his course is freely available online. You can go through the courses he is offering, and you can gain a lot of knowledge about computer science. Okay, so now this another example that I was talking about. So this is from his book, Tim Rough Garden's book, Algorithms Illuminated. Okay, so this searching two arrays, right? We are given two arrays, A and B. Two arrays are given, right? And we have to search that what will be the output. Output is we are looking for is that whether this A and B, A or B contains T. A or B contains T. So what I can write here, say this for I equals to 1 to n. Okay, and if AI, that means each of the array element being checked with that T. Okay, then if this is then true, then return true. So this we have checked that whether this is present in array, and then either of these A or B, if it is containing, then we have to output. So it may so happen that it is not there in AI. Okay, say AI is A is consisting of 10, 5, 1, 9, 7, something like this. Okay, and say B may be containing 5, so maybe different. We can take say 20, 15, 2, then 30, then 50. So this is the array, two arrays. Okay. So it may so happen that we are looking for 50 here, right? T equal to 50. So in that case, it may so happen that this T is not there in AI. Okay. Then we have to check that in this 1 to n. If bi, this array also we have to take into account, and then if this is this, then return true. So this could be the program that we can write for this. And now say we are trying to analyze this algorithm. Okay, we will be analyzing this algorithm. Analyze it. So how can we analyze this? Okay, so as we have seen that our target point is the for loop. Okay, and then within the for loop I am looking for that what exactly we are trying to check. We are trying to check whether this T is present here or here. That means each of the array element to be compared with T. So the bulk of the case, the bulk of the amount we are comparing in this program. So that comparisons will be taken as the representative one for analyzing this. So which statement is responsible for this? This statement. So if I am analyzing this, all other will be subsumed in that. Say this this will be order of n, this will be order of n, this will be order of 1. So if we add up this, say, for loop, we have seen that it is boiling down to order of 1. So if I am taking this, okay, this number of comparisons happening, how many times, then this way we can analyze this for loop as well. Okay, so it may so happen that, okay, this only one time I am comparing something. Okay, so in that case this will not be representative one, but for loop will be running n times. So at that time this will be the representative one. But in this case we are seeing that ai equal to t will be the target point, our target point. So this, how many number of comparisons happening in this for loop? This is, I can say that n. So in terms of number of comparisons, I can say that this is n. And how many times here it is happening? So here also n. Okay, so this will be number of comparisons is 2n. So we are having 2n number of comparisons, and some so we can write some other statements. If there's some other statements happening k times, k is constant, then I can take that into account as well. So in general we can have this structure, this 2n plus k here for this case. So this again I can say this for simplicity I am assuming that this is I am taking one time, this is I am taking one time. So instead of k I can write 2 here. We can analyze with k also, no problem. But for simplicity I am assuming, for better understanding right now, then whenever we will be going forward for other algorithms, at that time we will be analyzing with k here. K is constant. Okay, so 2n plus 2. Then I can write, okay, this is less equal to, say, 3n. This is less equal to 3n, right? And then this is our c, this is our gn. So we have to, for this order of n notation, if we have to bring it down to order of n notation, then this condition to be satisfied, fn less equal to c of gn, c times gn, right? So now this for n greater equals to n naught, that we have seen. So what could be the value of n naught? Can you identify here? Anyone? Can you identify what should be n naught? That means beyond which it will be satisfying. 2. Okay, yes, it is 2. So n naught will be 2. Very good. Who told n not equal to 2? You, Saurabh, and your name? Aditya. Aditya and Saurabh. Very good. You are attentive. All other attentive. All other also attentive, I guess. Okay, so this you see, it is getting satisfied with this. So we can write that this Fn equal to order of n. Okay. So here this for loop, and after that another for loop is happening. So it's some kind of additive operations going on. This for loop, whatever order of n, this for loop actually this also, this Fn equal to 2n plus 2 also we do not make. What we analyze, what way we analyze is this for loop is taking order of n time. So you see, our subsequent analysis will be, we will be doing like that. Okay, so this for loop is taking order of n. How? Because this comparison is taking order of n, right? And definitely this for loop, this statement will be executed order of n time. So this order of n behavior will not be changing. This for loop is taking order of n. So this time complexity will be Tn equal to order of n plus order of n, and this will be our order of n. And we will be very much happy with this, with a big smile, right? And we will be very much happy, right? With a big smile. Okay, so you see this this is actually we have got whenever we are searching one element, whether it is there in either in A or B. So now we are looking for checking for a common element. So checking for a common element. A common element in array A and B. Okay, element in A and B. So this problem we have got, right? So we can write this input and output. Input we are having this A and B with n, each one containing n numbers, and then output will be whether this whether or not there is an integer, there is an integer t which is there contained in both contained in both A and B, okay. So what we can write here is that for I equals to 1 to n we can do, and then for j equals to 1 to n do. Okay. If now we are checking if ai that will be checked with each of the element of, sorry, this is B, this should be B. So each of the element of this B, each of the index position, that means each of the element of AI, that means A array, will be checked with every element of this B. Okay, so that we will be knowing that okay, some element is there in both A and B. That is one possible implementation. You can think other in your hostel. So this is return true. If this is happening, then we have to return true. Then if we are coming out without, then we have to return false. Okay. So this is this thing, this guy. So this guy, this is the problem given by our John. So this guy is John. So John has given this problem to you, right? And now you have to analyze, okay? And his brother is there, and he's a little bit scared about this asymptotic analysis. So that's why he's a little bit disappointed, and say this guy is Bob. So John has given this, that you analyze this. What will be the time complexity of this, right? And Bob is little bit confused, but I guess you are not confused. Okay, you know how to do this, right? So what way you can do? We are targeting here. What we are doing again? We are doing the comparison operation. Okay, so for each of these element ai, so when I equals to 1, so it will be a1 will be checked with all bj's. Okay, so j equal to 1 to n. So for each of these I, how many times this this inner loop is being executed? How many times? N times. Okay, so how many times the outer loop is being executed? N times. So for each of these outer loop, n times a inner loop is being executed n time, right? So this statement, if this comparison will be executed how many times? Order of n square. Okay, so we can say that this n squared times. So this for loop, this double for loop, if we are getting the double for loop for I equals to 1 to n and j equals to 1 to n, then we are seeing that the representative this guy, this ai equal to bj is happening order of n square time, and that is contributing the bulk of this for loop contribution. Okay, that is given. So this for loop or this algorithm, overall the time complexity will be order of n square. So order of n square. Now see, if some expression is given, fn equal to say 2n squared plus 5n plus 2, okay, we can find out some expression like this. Somebody has unmuted, so please mute. Okay, so fn equal to this, if this is the case, then we have to do, we can figure out in detail analysis that how many times this loop being executed, how many times this loop being executed, how many this statement being executed, how many times this statement being executed, how many times this statement being executed, how many times this statement being executed. Okay, so like this way we can analyze also, and at that time the expression will be something like this. It may not be exactly like this, something like this. So 2n square plus 5n plus 2. Then I have to go by this this mathematical definition. That means it will be less equal to c times what is the highest index here, that is the 2. Okay, so this will be our gn, and sorry, this instead of gn I should be writing c times n square, or I can write here this 3 times n square. So what is the coefficient here? 2. So I can always safely take 3 as the valid one. 3 times n square. 2 plus, if I write that this fn, so if I write here this, okay, if I write here instead of 2, if I write this 2 plus epsilon n square, and epsilon greater than 0, then also this will be satisfied. Okay, so this 2 plus epsilon, always this 2 and then plus epsilon, our brain is not comfortable with that. So instead of that, we should take 3, just one more of this might be okay here, 3n square. Okay. And now can you tell me that if this expression is coming from this, and then it is, I am writing less equal to 3n square, this is our c, and this is our n square is the gn, then what will be the n naught? Can anybody say what will be the n naught? 6. Okay, I am trusting you. I haven't calculated. Okay, so n naught could be 6, as you are pointing out. Every other should check this in the hostel, right? Okay, so in that case, this fn is boiling down to order of n square, right? So here this for loop, double for loop, is boiling down to order of n square, that we have directly written here, Tn equal to order of n square, and this is the way we will be analyzing algorithms, right? This is the way we will be analyzing algorithms. And maybe another one I can write checking for duplicates. Okay, so another checking for duplicates elements. So you should be writing this right now, and after 2 minutes I'll be asking someone to answer this. So input is, this is array of n integers. Okay, and output is equal to this, whether A contains an integer more than once. Okay, so can you write your program and analyze and tell me? So you do it. I'll be arbitrarily asking 1 or 2, what is the answer? Okay, this problem is a very representative problem in computer science. Okay, at least as far as this analysis is concerned, because this analysis will be coming time and again in our course. Okay, this will be coming time and again. Who has done that? What you have to do? Anurag Mondal. Anurag, what will be the idea? How you will be checking duplicate elements? Mm-hmm. 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 Very good. Ah, okay. So I can take Anurag's idea, and uh, I can write, say, for I equals to 1 to n, we can do, and for j equal to this I plus 1, I plus 1, I plus 1 to n do, and then if ai, if ai equal to aj, then ai equal to aj, then return true, and then return false. So this is this could be the implementation. So here this A might be having 5, 10, 1, 9, 7, maybe something like this. B maybe equal to this. Oh, sorry, this only one. Okay, so this duplicate element, maybe this this is here 5. So this 5 here we are having, and 5 here, right? Okay. So this this thing, whether checking for duplicates, whether or not it contains an integer more than once, right? So for I equals to I, whenever I will be equals to 1, that means a1, this guy is to be compared with every other element. So that one possible implementation I am doing like this. You can have other implementation. Okay. So then this guy will be compared with every other, right? And then this guy will be compared with every other. So like this way it's going on. Okay. So when I equals to 1, j is starting from this 2 to n. That means it is starting from this 10 to 5. Okay. So this is one of the implementations, and if I am going by this, then what could be this? What could be the time complexity of this? Okay. So this time complexity, as you are telling, it is n square, order of n square. So how this is coming up, right? So you see this, this is for each of these, I am checking. Somebody has unmuted, so please mute. So I am taking this 5 as a point. Okay, this 5 as a point. This all others are points. All others. So I am checking this guy. That means this point with every other. So I am pairing this with this, then this with this, and then this with this, and then this with this. I am pairing numbers. And then this guy is being paired with this, with this, with this. Okay. So we can think of this, how many ways I can choose 2 out of n numbers. So this is this problem is boiling down to this. Okay. So this is, I guess, this is n choose 2. Okay. That means nc2. This is nc2, right? And we call that n choose 2, right? So this is our, this number of comparisons here happening is n choose 2. N choose 2. So what is n choose 2? n times what? N choose 2 nc2 n minus 1 by 2. Okay. So what will be the case? This n square terms is coming, n square minus n by 2. That means n square by 2 minus n by 2. So this again we can write that with that. So this could be our fn. If I am taking like this in isolation, n choose 2, fn equal to n choose 2, and then if I am writing this, then we can write with this c times n squared. C, you find out what could be the c in your hostel, right? And what could be the n naught. So maybe 1 will be doing here, 1 will be doing the trick, because this is n square by 2 and this is 1 times n square, that is n square. So this is n square by 2 minus some positive quantity, so it will be definitely less equal to 1 times n square. Okay. That means n square, definitely. So we can say, by going by the definition of order of going by the big O notation, so that order notation we call big O, right? So big O notation we call. So this is, and also as we are taking this is less equal to, that means we call this as upper bound as well, upper bound. Okay. This is very important term for computer science, upper bound and lower bound. So that means I am telling, say, fn less equal to 10. That means fn could be at max 10, at max. This is the upper bound. Okay, something like this. So fn less equal to c times n square. That means at most, or c, if c is 2n square, at most that. Okay. So this is the upper bound we are having. So this is, so I can say right now that this for loop will again be boiling down to order of n square, right? Order of n square. So this is the way we analyze algorithms. And whenever, so as you can sense, the rest of the course will be heavily dependent on for loops. Okay, heavily dependent on this for and while loop. And whenever the loop is coming, by this time I guess you know how to analyze this. So we'll be directly writing, we'll be directly targeting the for loop, because that will be consuming the bulk of the time. We'll be directly targeting the for loops or while loops, the looping structure, and we'll be trying to find out the time complexity of any algorithm. So today up to this, if you have any question, you can ask me.